Imagine trying to upgrade a massive AI model's memory,
Right.
but you're not doing it by just throwing another $1 billion worth of silicon at it.
Yeah, no more buying massive clusters of NVIDIA chips just to brute force the problem.
Exactly. I mean, if you follow AI hardware even a little bit, the physical limits we are hitting right now, with power consumption, silicon yields, all of that. So today we are doing a custom-tailored deep dive into an engineering effort that tries to sidestep that physical wall entirely.
And they're doing it by fundamentally changing the underlying laws of mathematics that the model uses to actually think.
Right. We are looking at the Shannon prime inference engine. Specifically, we're digging into a massive architectural shift that they call the Friedman stack.
And I have to say, the documentation we are reviewing for this today is incredibly dense.
Oh, yeah. It's intense.
I mean, we are looking at their internal engineering specifications, the mathematical proofs justifying the whole architecture, and, the raw system benchmarks. The overarching goal of our deep dive today is to evaluate the exact criteria required to ship this Friedman stack as a default production-ready engine feature.
Which is a huge deal, because what they're attempting to do here is essentially replace the standard continuous floating point mathematics of AI memory with discrete topological trees.
Right, which sounds abstract, but it's a shift that promises massive compression, perfect mathematical stability, and perhaps most importantly, zero drift.
Zero drift is literally the holy grail. I mean, if you have ever tried to run a local language model on your own machine, and you've noticed it slowly losing the plot during a really long conversation, like it gets confused or starts hallucinating.
Yeah, it just forgets what you were talking about 20 minutes ago.
Exactly. And a huge part of that is mathematical drift. So to really understand the shipping criteria for the Friedman stack, we have to look at the bedrock mathematical environment they're building from the ground up. Standard AI math relies entirely on floating point arithmetic.
Yes.
It's continuous, sure, but more importantly, it is fundamentally blurry.
Blurry is a really good word for it. It is inherently blurry because floating point arithmetic on a standard GPU is just not truly associative.
Right, the order of operations messes it up.
Exactly. I mean, in pure math, if you add A plus B and then you add C, you get the exact same result as adding B plus C and then adding A. That's just basic algebra.
Right.
But when you are dealing with 16-bit or 32-bit floats, the computer has to round off these microscopic decimals at every single step just to fit the numbers into physical memory. So A plus B plus C might actually give you a slightly different value at, the millionth decimal place than A plus B plus C.
And in isolation, who cares about the millionth decimal place?
Yeah, right, exactly. But in a transformer model with billions of parameters, doing trillions of operations across 96 different layers, those microscopic rounding errors cascade.
They accumulate.
Yes, they accumulate, and that is what drift is. The actual mathematical foundation of the model's thought process physically degrades over time.
It's like you're building a skyscraper, but every time you add a floor, your ruler shrinks by a fraction of a millimeter. By the time you get to floor 90, the windows don't fit into the frames anymore.
That is a perfect analogy, and the Shannon Prime team's answer to this isn't to just buy a more precise ruler like moving to 64-bit floats.
Right.
Their answer is to stop using rulers altogether and switch to interlocking bricks. They are moving the transformer's entire hidden state into a framework based on a complex multiplication elliptic curve.
Okay, now we're getting into the heavy math.
Yeah, specifically, they're operating over an imaginary quadratic field. And the core engine of this entire thing is a very specific number. It's the Heegner number, -163.
-163. Why that specific number? I mean, what makes -163 the magic key here?
So, operating over the field denoted as q adjoin the square root of -163 is what guarantees absolute algebraic stability for the system.
Okay.
The reason this specific Heegner number is the absolute linchpin of the whole architecture is that it possesses what mathematicians call a class number of 1.
A class number of 1.
Right. And that dictates that its ring of integers forms a unique factorization domain, or a UFD.
Okay, let's ground that a bit for the listener. So we enforce a unique factorization domain to basically guarantee that every matrix multiplication in the neural network collapses into one and only one canonical state.
Exactly one, yes.
Because with standard integers, the number 12 only factors into prime numbers one way. It's 2 times 2 times 3. There's literally no alternate universe where 12 factors into something else.
Right, that's just basic arithmetic.
But when you move into complex number fields, you often lose that property.
Right.
Right? A mathematical state might actually factor in multiple different ways depending on how you approach it. And the moment that happens in an AI.
You lose determinism
Hmm.
completely. You introduce ambiguity into the core logic gates of the intelligence.
Which is terrifying if you want a stable system.
Exactly. So by using Hegner -163 and securing a UFD, every single linear algebraic step of the AI's inference process can be expressed exactly in integers.
Everything, the projections, the attention mechanisms.
Yes, all of it. Layer normalizations, everything. There are 0 decimals to round off. There is absolutely no microscopic variance. Exact mathematical inverses exist for every single map in this space.
Wow. So if you transform a vector forward, you can mathematically transform it backward and arrive at the exact bit you started with.
The exact bit, yes. The operations are perfectly lossless on their own algebra.
So going back to our analogies, instead of a smooth, continuous volume slider, where you can never quite hit the exact same decibel level twice because your thumb shakes slightly. Right. The system now operates on a heavy mechanical dial. You know exactly what notch you are in, and there is physically no space between the notches. The mathematical state moves from point to point on this elliptic curve without ever accumulating a single fraction of drift.
Which is an incredible foundation. But since we have established this perfectly discrete notched dial, we immediately have to address the physical limits of the dial itself.
Right, how many notches are there?
Exactly. The Shannon prime framework uses complex multiplication theory, or CM theory, to define strict, mathematically provable information capacity limits for every single layer of the AI.
And they govern this limit using something called the Haswell bound.
Yes, the Haswell bound.
This is where it intersects directly with standard Shannon limits of information theory, which I find fascinating. The documentation gives the explicit formula for this bound. It is n of p is less than or equal to p plus 1 plus 2 times the square root of p. And this formula determines the absolute maximum number of distinct hidden states that are mathematically reachable at any single layer of the transformer.
So let's unpack the mechanics of that formula real quick. The p in there represents the specific prime number they are using for their arithmetic modulo.
Right, it's their mathematical sandbox for that specific channel.
Exactly. So the Haswell bound dictates the geometry of the elliptic curve over that finite field. The p plus 1 gives you the baseline number of points on the curve, and that 2 times the square root of p acts as the theoretical variance, or the maximum allowable deviation.
Okay, so when you map this to AI architecture, what does it actually do?
It acts as a fundamental hard-capped limit for the transformer's capacity to hold information. It is the Shannon limit of the channel.
Okay, so the documentation actually runs an example to show this in practice using the prime p equals 41.
Yes.
If you plug 41 into the Haswell formula, the maximum capacity per coordinate per layer works out to exactly 5.78 bits.
Right, around 5.78.
But hang on, 5.78 bits is tiny. I mean, if you follow standard open source models right now, you know they typically run on 16-bit floats. And we are really just now seeing 8-bit quantization become standard for running things locally.
Very true.
So if we hard cap the model's capacity, roughly 5.8 bits per coordinate, aren't we just severely bottlenecking the AI? I mean, it feels like we're stripping away the model's ability to hold on to nuance.
Well, it only looks like a bottleneck if you assume all 16 bits of a standard float actually contain useful information.
Oh, and they don't.
They absolutely don't. The restriction to 5.78 bits doesn't bottleneck the AI. It forcefully filters statistical noise.
Interesting.
See, standard models using 16-bit floats are overwhelmingly just memorizing garbage variants in those lower decimal places.
Yeah.
They're literally trying to assign semantic meaning to the equivalent of microphone static.
Okay, so the 16-bit float is like a microphone that's way too sensitive. It's picking up the hum of an air conditioner 3 rooms away, and the AI is wasting massive amounts of compute trying to figure out what the hum actually means in the context of the prompt.
Exactly. The Haswell bound acts as a harsh mathematical noise gate. It only lets the actual semantic signal through. It forces the network to only encode what is mathematically novel.
Wow.
The theory literally proves that if the trajectory of the inference process visits the maximum distinct states at layer L, it mathematically cannot extract any additional information at layer L plus 1.
Because it's already full.
Right. The model's expressive capacity is rigidly physically bounded by the theorem. And this is what perfectly validates the entire framework against classical Shannon channel limits. It mathematically defines the maximum rate of error-free transmission through the transformer.
And because we know the absolute maximum limit of the signal now, we can compress the model safely without destroying it.
Which brings us perfectly to quantization.
Right. Because if you are a developer trying to squeeze a massive 70 billion parameter model onto a consumer graphics card, you have to quantize it. You have to lower the
I'll
precision.
have to make the model smaller.
Exactly.
Yeah.
And usually you use a standard method like AWQ or GPTQ, but that process is inherently destructive. You basically take a mathematical chainsaw to the weights to make them smaller, and doing so destroys the really delicate multiplicative relationships that the model learned during its training phase.
Yes, you are actively breaking the model to shrink it.
Right. And to fix it, you have to run a calibration pass. You pump 1,000 samples of text through the broken model. You see where it hallucinates or spits out garbage. You calculate a Hessian matrix of all the errors, and then you try to glue the parameters back together so it somewhat functions again.
Calibration is basically a giant Band-Aid for unpredictable rounding errors.
Yeah.
But in the Shannon prime engine, because of the math we just talked about, they use a methodology called Sato-Tate mixed precision. And this methodology completely eliminates the need for any calibration data whatsoever, zero calibration.
Shrinking the model perfectly without needing a single test pass to see if you broke the intelligence. I mean, how does the math actually allow for that?
Well, because the model operates entirely on that complex multiplication curve we established earlier, lowering precision is not achieved by just rounding off numbers.
Okay.
It is accomplished by iterating a structural mathematical transformation called the Frobenius endomorphism.
That's a mouthful.
It is. An endomorphism is essentially a mapping of a mathematical structure onto itself that strictly preserves its algebraic properties.
Okay, so it shrinks it without changing the shape.
Exactly. And the absolutely critical mechanic here is that the Frobenius endomorphism commutes with the layer operations of the neural network.
Okay, let's clarify. Commutes,
Hmm?
meaning the order of operations doesn't change the final outcome.
Yes. You can apply the transformer's heavy layer multiplications and then apply the Frobenius reduction. Or you can apply the Frobenius reduction to shrink the precision first and then run the layer multiplications.
And the result is identical.
Mathematically identical. Lowering the precision via this method preserves the algebraic relations flawlessly. There is literally nothing broken to calibrate.
That is wild. And to execute this practically, the documentation says the Sato-Tate mixed precision leverages the specific behavior of prime numbers within this Heegner field.
Right.
Because primes here exhibit two very distinct behaviors. They either split or they are inert.
And this is where the mixed precision architecture gets its name. So inert primes, for example, the prime p sub 1 equals 2. They provide absolute zero drift quantization.
Zero drift at all?
None. The underlying math dictates that their Frobenius traces are strictly zero. There's zero variance.
Okay.
But split primes, like the p sub 2 equals 41 that we discussed earlier, they do have variance, but they possess a bounded analytic drift.
Bounded because of the Hasse-Weil limits.
Exactly.
So it's essentially a hybrid engine. You pair a 2-bit channel using the inert prime, which is like your electric motor, perfectly clean, zero variance, zero emissions, with an 8-bit channel using the split prime.
Yes.
And the split prime is your gas engine. It generates some exhaust, some variance. But because of the Hasse-Weil bounds, we know the exact mathematical maximum of that exhaust before we even turn the engine on. We don't need to test drive it 1,000 times to see how it will perform.
Exactly. By mathematically combining that 2-bit inert channel and the 8-bit split channel, the engine creates a 10-bit mixed precision format. They call it FP10.
Right.
And this FP10 format is entirely variance-free regarding unpredictable drift. It requires absolutely zero calibration data to deploy. It just works.
Okay, so we have proven we can compress the math without drift. We have our notch dial, we know exactly how many notches it has, and we know we can shrink it safely using Sato-Tate. But now, we hit a massive physical reality wall, because the engine has to translate messy, unpredictable human language. You know, the prompt you actually type into the chat box into this pristine, discrete mathematical environment, and it has to do it in real time.
Yes, that is the hard part.
How does it actually convert a typed prompt into an algebraic state? And that is the job of the very first tier of the Friedman stack, the KSTE, the Knight-Spiner tree encoder.
The KSTE is brilliant. It bridges the continuous world and the discrete world.
Okay, walk me through it.
So the standard input to an AI attention mechanism is a key vector. That is typically a continuous 128-dimensional array of decimal numbers representing the semantic weight of a single token.
Right, like the word apple becomes a list of 128 decimals.
Exactly. The KSTE takes that continuous 128-dimensional key vector and it structurally converts it into a discrete 60-node topological tree with 3 specific labels.
So it literally turns a list of numbers into a branching tree. Normally, an AI looks at a 128-dimensional vector, like a dense cloud of decimal points floating in space. But the KSTE strips away the cloud and just hands the system the solid constellation lines. It discards the exact numerical scalar values entirely.
Completely throws them out.
It only looks at the order pattern, the ranks of the absolute values, and whether they have a positive or negative sign.
And discarding those exact scalar values is the absolute key to maintaining the algebraic stability we achieved with the complex multiplication earlier.
Oh, because if you kept them.
If the KSTE preserved the raw floating point decimals, it would immediately reintroduce the non-associative drift we literally just spent all this math eliminating.
Right, you'd be right back to blurry math.
Exactly. By relying purely on the rank and the sign, the encoder guarantees bit-identical tree construction. The conversion process is entirely deterministic.
But wait, if we throw away the exact numbers and just keep the rank like this value is the biggest, this one is second biggest, don't we lose the specific magnitude or the loudness of a semantic feature?
What do you mean?
Well, say the vector dictates that the concept of urgency is at a level of 100 and politeness is at a 2, versus another token where urgency is at a 5 and politeness is at a 4. The rank is identical in both cases, right? Urgency is number 1.